Okay, so we're all living in the middle of this incredible AI boom. I mean, it's everywhere, powering our search results, driving our cars, the whole nine yards. But behind all that digital magic, there's a massive physical cost that we don't really talk about. And that's exactly what this really clever research paper digs into, and it offers up a pretty brilliant solution. So, what are we talking about here? What is this hidden cost? We see all the amazing things AI can do, but have you ever stopped to think about what it actually takes, physically, to make all that happen? Well, it's not just about fancy algorithms or endless lines of code. The real challenge, that hidden cost, it's all physical. We are talking about absolutely massive amounts of energy, huge memory requirements, and this relentless demand for bigger, better, more powerful hardware. And that really gets us to the heart of the matter, AI's hidden power problem. It's a really big deal, and it's a challenge that one team of researchers decided to tackle head-on. See, training one of these deep learning models, it's just an incredibly intense process. It creates this gigantic memory footprint. You need all this specialized, super expensive hardware to run it. And guess what? All that gear just guzzles a staggering amount of electricity. That's kind of the brute force reality of where modern AI is at right now. So what's behind all this inefficiency? Well, to get that, we've got to look at something really fundamental, something we kind of take for granted, the way computers actually represent numbers. Turns out, the problem lies with the standard formats we've been using for decades. Okay, for decades, the go-to industry standard for numbers in computers has been this thing called the IEEE floating point format. Now, don't get me wrong, it's incredibly precise, which is awesome for a lot of things. But for the millions upon millions of calculations that happen in AI training, it's also really bulky and just hogs resources. It's a huge part of the problem we're talking about. There's a great way to think about this. Using that standard format for AI training, it's like using a sledgehammer for a job that just needs a tiny little tack hammer. Sure, you'll get the job done, but with a whole lot of wasted effort and energy. And that sledgehammer, that's our 32-bit standard. All that precision we talked about, it takes up a ton of space and burns through energy. And for years, that's just how it was done. It was the only way. But what if there was a better way? A tack hammer for our AI job. Well, this is where the hero of our story comes in. A much smarter number format called the posit. So the posit is a pretty new way of doing things. It's a numerical format that was literally engineered from the ground up to just be more efficient. Its whole design is way more flexible and compact, and it's specifically tailored for the exact kinds of calculations that are happening inside a neural network. Basically, it's designed to be the right tool for the job. And this comparison just nails it. The old floating point standard is like writing out $1 million. Yeah, it's accurate, but it's kind of clunky, right? The posit format, on the other hand, is like writing 1M. You're getting the exact same essential information across just way more efficiently. Okay, so this all sounds fantastic in theory, right? But the real question is, does it actually work for training a really complex AI? Well, the researchers put it to the ultimate test in what they called the 8-bit training test. This is where the rubber meets the road. And this was the central question, the big one they really needed to answer. Could they actually train a powerful, accurate AI model using these tiny, super compact 8-bit posits instead of the big, bulky 32-bit standard? I mean, that was a really bold question, and the answer had huge implications. So they put it to the test. A team of researchers, and hats off to them, Gonçalo Raposo, Pedro Tomás, and Nuno Roma, they documented their whole groundbreaking experiment in this paper, titled PositNN. They really set out to see if this new, super efficient number format could actually hold its own against the old champ. And their approach was really systematic. Here's how they did it. First, they built a special software framework just to simulate using these little low-precision posits. Then, they ran a complete end-to-end AI training process. And finally, the most crucial step, they compared the accuracy of their 8-bit posit model directly against a model trained the old-fashioned way, with the 32-bit standard. And the results of that comparison? Well, they bring us to our final section. And let me tell you, they have some seriously profound implications for the future of AI. It's all about smaller numbers and a much bigger future. Get this is the money quote, right from the paper's abstract. The results were a total resounding success. They discovered that 8-bit posits can substitute for 32-bit floats during training with no negative impact on the final loss and accuracy. Let that sink in. No negative impact. That is a huge, huge discovery.
So let's just remember the old way for a second. 32 bits. Big, bulky, power-hungry, and not very efficient. And now, look at this, the new possibility. 8 bits. That is 4 times smaller. This right here just shows you the incredible scale of the efficiency gain they proved was possible. It's a truly monumental leap forward.
So why is this such a big deal? Well, it means a drastically smaller memory footprint. It means AI can run on cheaper, much less demanding hardware. It means way lower power consumption. And you know what that all adds up to? It makes powerful AI more accessible to everyone, not just the big tech companies with giant data centers.
Which leaves us with one last really exciting thought. Think about it. By making the fundamental building blocks of AI 4 times smaller, we've just removed a massive bottleneck. So the real question isn't just about efficiency anymore, it's about potential. If we can shrink the numbers this much, just how big can AI get?